Hello students, good evening everyone. I hope all are doing well. Welcome to Infinity Learn by Sri Chaitanya JEE YouTube channel. This is Miss Surya, your chemistry faculty from Infinity Learn. If anyone is watching this particular live, just give me hi in the comments. Just mark your attendance here. Finally, we will be moving to our last part of the same chapter, solution. That's about the last part of colligative properties here. Okay, the last class we have discussed the other three colligative properties, right? We are starting from the Okay, before that, what do you mean by diffusion process? What do you mean by a diffusion process given here? Hi Arcade, good evening. And I hope I am perfectly audible and visible to everyone. Is there any issues are you facing? Okay, what do you mean by the diffusion process? What do you mean by the diffusion process? And only we can talk about the osmosis and osmotic pressure here. What do you mean by the diffusion process? As we already know, right? The spontaneous flow of particles from high concentration to lower concentration region is known as a diffusion. For example, if I am taking two beakers here, right? This will be our parting. I am separating it with a membrane here. This red one will be our membrane. If I am saying this is the first one having the concentration of C1 and this is the second one having the concentration of C2, right? If I am saying the C1 is always greater than C2, C1 is always greater than C2, what will be the particle movement there? Is it is moving from C1 to C2 or C2 to C1? Okay, Arcade, thanks for the confirmation. C1 is greater than C2, right? Which means solute is more here. Okay, in terms of solute and solvent concentration, we can define this as a C1 and C2 where C1 is greater than C2, right? So what will happen to the particles? Where they will move? From first part to second or second to first? Obviously, it will move from C1 to C2, right? C1 to C2. That is the spontaneous flow of particles from high concentration to lower concentration. Such a process is known as diffusion through a membrane. This is our membrane given here. I hope you understand what you mean by the process of diffusion. Clear? Is that clear? Just let me know in the comments. Okay. Now let us talk about the process of osmosis. It is also a type of diffusion in which the particles are moving from low concentration to higher concentration through a semi-permeable membrane. Semi-permeable membrane, right? The process of solvent flowing into the solution when the solvent particles are separated by a semi-permeable membrane. Then the next question will be, what do you mean by semi-permeable membrane? What do you mean by semi-permeable membrane? Let us see what you mean by the semi-permeable membrane. Yes. It is a specific type of membrane which allows the movement of a specific type of particles. For example, if you are taking a solution, it allows the movement of solvent particles only through it. Such a membrane is known as a semi-permeable membrane, which is used in the case of osmosis, process of osmosis, right? So, in general, parchment paper cellophane paper, pig's bladder, and some of the inorganic precipitate like copper ferrocyanide papers are used as a semi-permeable membrane. Clear? What do you mean by semi-permeable membrane? Is that clear? Right. Let's come back to the osmosis process here. Similarly, if I am taking the same process here, same process, here I am separating it by a membrane like this. Again, the concentration is C1. This is the concentration C2. If C1 is greater than C2, if C1 is greater than C2, right? So, solute will be more here. Solvent will be less here, right? Concentrated solution. Then in this case, solute will be less, solvent will be more, right? That is the dilute solution. So, as according to our definition or the process of semi-permeable membrane, Prashant Soni, flow of particles from high concentration to low concentration. Yes, that is the process of diffusion, right? If you are talking about the osmosis process here, one point you have to keep in mind that it is the movement of solvent particles from low concentration to high concentration, right? Which means dilute solution to concentrated solution. Let me detailing explain. So, if you are taking here in this particular case, C1 is greater than C2, which means solute is more here, right? Solute is more here in the case of C1 and solute is less in the case of C2. According to our semi-permeable membrane, this red marked one is represented as the semi-permeable membrane. It will allow only the flow of solvent particles, right? Flow of solvent particles. In this case, among C1 and C2, which one is having the higher concentration of solvent? Higher concentration of solvent. Give me the answer. In C1 and C2, which one is having the concentration higher in case of solvent? In case of solvent. I hope my question is clear. So, if you are checking here, you can say that this is a C2 having less concentration in terms of solute, which means that it contains more solvent particles. So, obviously, it will move from this side to this side, right? C2 to C1, which means we can say that the particles will move from low concentration to high concentration through a semi-permeable membrane. That process is known as osmosis. I hope it was clear. Prashant, are you getting confused again? Diffusion is a process in which there is a simple membrane which allows the movement of particles from high concentration to lower concentration. That is a type of diffusion. But in the case of osmosis, it allows the flow of solvent particles, right? It allows the flow of solvent particles. So, as general, it is a diffusion in which solvent particles will flow from their higher concentration to lower concentration, right? Solvent will move from their higher concentration to lower concentration. But we are explaining this in terms of osmosis. We can say that if you are explaining in the terms of solute, we can say that the flow of solvent particles from low concentration to higher concentration through a semi-permeable membrane is known as the osmosis process. I hope it was clear. Is that clear now? Right, clear? So that we can just define the osmosis as the process. The spontaneous flow of solvent particles from solvent to solution side, right? Solvent to solution side or low concentration to higher concentration side through semi-permeable membrane, right? That is the process of osmosis. Fine. Now we will be moving to our colligative property, that is the osmotic pressure. What is the osmotic pressure, right? So, in the similar case, if you are applying an excess pressure to the solution side, what will happen that it will stop down the osmosis process, right? It will stop down the osmosis process. For example, same case we have to take in here. Semi-permeable membrane, C1 versus C2, right? C1 versus C2. What will happen here? The solvent particles will move from low concentration to high concentration until an equilibrium reaches, right? Till then they will start flowing the particles from the solution side to solvent side, right? Otherwise low concentration to high concentration side. Then if I am applying an extra pressure to the solution side, what will happen? The process of osmosis will prevents or stops. That particular pressure we are applying is known as the osmotic pressure of the solution. Is the thing clear? Okay, this is a better image given here. Right? This is our solution side, this is our solvent particle. It should be connected by a semi-permeable membrane. SPM stands for semi-permeable membrane. Then, this is a normal pressure given here. If I am applying an extra pressure, an excess pressure, it is denoted by letter pi, that is our osmotic pressure. If I am applying an excess pressure to the, which side? Solution side, right? Which I am applying to the solution side, what will happen? The process of osmosis prevents. That particular pressure we are applying is known as the osmotic pressure of the solution. I hope you guys have understand. Clear? Generally, osmotic pressure is represented by the letter pi. Okay, fine. Now, we need to do the numerical calculations, right? If you are talking about the dilute solution or the ideal solutions, this osmotic pressure, pi, is always proportional to the temperature. As the temperature increases, osmotic pressure also increases, right? That is the one condition. Similarly, if you are talking about the concentration, the osmotic pressure is also depends on the concentration. So, pi is proportional to C. So, this osmotic pressure depends upon the concentration as well as temperature. As the temperature increases, osmotic pressure also increases. As the concentration changes, osmotic pressure also changes. So, we can just define the equation as pi is equal to ZRT, where C is the concentration of the solution, R is the universal gas constant, T is the temperature. Then, what we have to do? We need to find out the molar mass of the solute, right? Molar mass of the solute. So, we are just elaborating the equation as W by M into RT by V. Right, W by M into RT by V. Here C is taken as N by V, where molarity. If you are taking the value of N is given here, it will be W by capital M, where W is the given mass. W is the given mass, weight of the solute, and M is the molecular weight of the solute, where V is the volume of the solution in liters. If you are substituting the values here, you will get the value of M as the molar mass of the solute. Clear? Is that clear how we are calculating the molar mass of the solute by using the term osmotic pressure? Then, in many of the JEE Main question, it was asking about the one word question about like that. Which of the colligative property is used for determine the molecular masses of proteins, polymers and other macromolecules? So, you need to keep in mind that this is the only one colligative property which is used to find out the molecular masses of all the macromolecules, including proteins, polymers and everything. Right? So, osmotic pressure will be the correct answer for that question. Clear? Now, the process of osmosis is clear. I hope it was clear. Now, let me talk about the another process, that is a reverse osmosis. What do you mean by reverse osmosis? What the name suggests? Reverse osmosis. The osmosis which is happening in the reverse manner, right? Osmosis happening in the reverse manner. So, for example, this is our condition given here, saline water, salt water. If I am applying a pressure greater than osmotic pressure, if I am applying a pressure greater than osmotic pressure, what will happen? In general, the osmosis will happen from low concentration to high concentration, right? Low concentration to high concentration. If I have application for that, we need to apply a pressure higher than the osmotic pressure to the solution side. Clear? So based on the reverse osmosis, we can desaline used for the desalination of seawater, right? Desalination of seawater is the application of reverse osmosis. Now let us divide the solutions according to the osmotic pressure condition. For example, if I am taking two solutions having the same osmotic pressure, for example, pi 1 is equal to pi 2, which means same osmotic pressure. So I can call this particular solution as isotonic solution. Isotonic solution, right? Isotonic solution. Then, if pi 1 is greater than pi 2, which means one of the solutions is having higher osmotic pressure than expected, then I can call this particular solution as hypertonic. Hypertonic. Then if pi 1 is less than pi 2, what I can call this as, this will be hypotonic solution. Hypotonic solution. So can anyone please give me an example of an isotonic, hypertonic or hypotonic solution from real life? Anyone? Based on the osmotic pressure, we have divided the solutions into three types. One is isotonic, which means both the solutions having the same osmotic pressure. If one of the solution is having one of the solution having higher osmotic pressure as from the first one, it will be called as hypertonic. If one is having less osmotic pressure compared to the one, then it will be calling as hypotonic solution. In the case of hypertonic solution, I hope you must have seen about the making of pickle, right? If you are taking mango pickle, you are adding in the saline water, right? What will happen after few days? What will happen after few days? So, as a part, this is the application of hypertonic solution there. Water will go from inside to the cells, then it will happen the strings of the solution. Then, is there any other example? If you are talking about the hypotonic solution, obviously there will be a swelling happens, right? Swelling happens. From the outside side, water will come inside, so swelling happens. So this is the condition for the different type of solution, isotonic, hypertonic and hypotonic solution based on the colligative property osmotic pressure. I hope you guys understand. Finally, we have covered about all the colligative property. What are the different colligative properties we have already covered? first one, relative lowering of vapor pressure, right? Relative lowering of vapor pressure. For example, if you are adding any of the non-volatile solute to the solution, what will happen to their vapor pressure? Vapor pressure decreases, right? So that particular colligative property is named as the relative lowering of vapor pressure. It is given as delta P divided by P0, where P0 is the vapor pressure of the pure solvent, right? That will be equal to the mole fraction of the non-volatile solute. Mole fraction of the non-volatile solute. So this will be the equation to calculate the concentration of the solute by using the first colligative property, that is relative lowering of vapor pressure. Then what about the next one? Elevation in boiling point, right? If you are adding, similarly, if you are adding non-volatile solute to the solution, vapor pressure decreases, obviously boiling point also increases. So that will be the difference in the elevation in boiling point. The name itself says that there will be the increases in the boiling point of the solution. So it will be given as delta TB is equal to Kb into molality, where Kb is the constant, molal elevation constant, right? Then small letter m is the molality given here. This is the formula to calculate the molar mass of the solute by using the elevation in boiling point of the solution. Then how we can calculate delta TB there? How we can calculate the delta TB there? TB minus TB naught, right? TB is the boiling point of the solution. TB naught is the boiling point of the pure solvent, right? It will be always higher than the solution. So TB minus TB naught will be the value to calculate the delta TB here. Then what about the next one? Depression in freezing point. Vapor pressure decreases, so that freezing point also decreases. That is the name suggests the depression in freezing point of the solution. Similarly, it is also proportional to the molality of the solution. So we can given it as delta TF, that is our depression in freezing point, is equal to the a constant, molal depression constant into molality, right? How we can calculate delta TF here? TF naught minus TF, right? TF naught minus TF. This is the important thing you have to keep in mind before doing the calculations. Then the last one, our osmotic pressure, right? Osmotic pressure represented by letter pi, that is equal to CRT, where C is the concentration. Generally it will be in the molarity terms. R is the universal gas constant, T is the temperature in Kelvin. I hope it is clear. Now, as so far we have discussed about the colligative properties of the solution, right? It is all about the non-electrolytes. If you are talking about the electrolytes, right? There will be a chances of association or dissociation, right? Association or dissociation happens. In that terms, what will happen to the colligative property? Obviously the number of particles changes, right? Number of solute molecules changes due to the association or dissociation of the molecule. So that colligative property also changes. That particular term is known as the abnormal colligative property. Abnormal colligative property. Is that clear? If you are talking about any of the electrolytic solute, they can be either dissociate or associate in case of a solvent. So it will lead to the increase or decreasing in the number of solute particles, right? As a part of that, actual value of colligative property changes from the original or theoretical value, right? That is the abnormal colligative property. Now let us talk about how they are affected by the association and dissociation, right? So for that we are introducing a new term known as I, otherwise known as Van Hoff factor. Van Hoff factor, which is defined as the ratio of observed colligative property divided by calculated colligative property, right? So that we are just changing all the colligative properties by multiplying with the Van Hoff factor. For example, if we are taking delta TB here, right? That is our elevation in boiling point. In terms of abnormal colligative property, it will be equal to I, Van Hoff factor, into Kb, where Kb is our constant, into molality. Clear? So the final equation will become for the relative lowering of vapor pressure I into mole fraction of the solute. Then for delta Tb, I into Kb into m. For delta Tf, it is equal to I into Kf into m. And then final for the osmotic pressure is equal to I into CRT. Just multiplying with the Van Hoff factor, you will get the abnormal colligative properties there due to the association or dissociation of the molecules or the solvent. Now let's see how the association or the dissociation of the particles affecting in the case of colligative properties, right? So in general, we can take an example given here, right? KCl or NaCl, it will be dissociates into K plus and Cl minus, right? K plus and Cl minus as the ions here because it is an electrolyte, strong electrolyte, right? So it will be changing into K plus and Cl minus. If I am taking the initial condition, for example, at T equal to 0, the complete concentration or the number of moles will be 1, right? Initially it will be 1. Finally it will be, here it will be 0, 0, right? Initially. At equilibrium or T is equal to a definite time. Dissociation happens, right? Dissociation happens if I am introducing the term alpha here. Alpha means our degree of dissociation. What will happen to the initial stage KCl? It will be 1 minus alpha, right? 1 minus alpha. From number of moles of 1 here, alpha is dissociating. So 1 minus alpha, then it will be alpha and alpha, right? Alpha and alpha. Similarly, if you are taking a general condition here, n number of molecules get converted into AN. Then initially it will be 1. Initial moles is equal to 1 in the case of Na. AN it will be 0. If you are doing any of the association, any of the dissociation here, right? Dissociation, it will be taken as 1 minus alpha. Then finally it will be N alpha. For example, here it will be 2 alpha, right? 2 alpha. 1 minus alpha and 2 alpha. Right. Now we need to find out the total number of moles. Total number of moles after ionization. After ionization, what is the total number of moles given here? Sum of these two, right? 1 minus alpha plus N alpha. 1 minus alpha plus N alpha. If you are solving here, you will get the value is equal to 1 plus N minus 1 into alpha. Is that clear? 1 plus N minus 1 into alpha. That will be the number of particles after ionization. Ankita, is there any issues? Okay, I hope there is no any issues. Maybe in audio and video, everything, it will be fine. Okay, the total number of moles after ionization is equal to 1 plus N minus 1 into alpha, right? Then, for Van Hoff factor, there is another equation to find out Van Hoff factor, that is in terms of ionization or association or dissociation, we need to calculate the Van Hoff factor as total number of moles after ionization or the association or dissociation divided by total number of molecules before ionization or association or dissociation, right? Based on that, we can calculate the Van Hoff factor as total number of particles after ionization is 1 plus N minus 1 into alpha, right? Before ionization, it will be 1 plus 0, that is equal to 1. So we can define the Van Hoff factor I is equal to 1 plus N minus 1 alpha divided by 1, that is equal to 1 plus N minus 1 into alpha. So this will be the Van Hoff factor in case of dissociation. In case of dissociation. So if you are talking about this case, right? If you are talking about the case of KCl, what will be the Van Hoff factor? 1 plus n minus 1 into alpha, right? Where n is the total number of ions get ionized. Total number of ions forming after ionization. It will be 1 K plus and 1 Cl minus, right? Total 2 ions are forming after ionization. So Van Hoff factor is equal to 1 plus alpha for KCl. I hope it was clear. So from that we can find out the value of alpha is also given here. If you are taking here, it will be I minus 1 divided by n minus 1. That will be the value of degree of dissociation or degree of ionization. That is the case for the association of the molecule. So that Van Hoff factor changes. We will get a Van Hoff factor according to the value of degree of association. So that colligative property also changes. Clear? So what will happen in the case of dissociation? The number of solute particles increases, right? For example, if you are taking 1 mole of KCl, you will get 2 moles, 2 particles, right? K plus and Cl minus. The number of solute particles increases, then colligative property also increases, but molar mass decreases, right? Molar mass decreases. Yes, molar mass of the solute decreases. That is the case for degree of dissociation of the solute particles, right? Now, what about the next condition? Association of the particles, effect of association. Same case I am taking here. N number of particles, Na particles are converting to A into N, right? An. For example, if I am taking 2A molecules as A2, it get dimerizing, right? 2A particles will be changing to A2. For example, if I am taking A here, it might be changes by A by 2, right? 2A will be changes to A2 or A might be changes into A by 2, right? A by 2. For example, if I am taking degree of association as alpha here, then it will be alpha by 2, right? So here I am changing here. 1 minus alpha is the after association, 1 minus alpha is here. For n particles, it will be alpha by n. N is the number of particles forming here. So, again we need to find out the total number of moles after association. Not about dissociation, it is about the association here. About association. Total number of moles after association is equal to 1 minus alpha plus alpha by n, right? 1 minus alpha plus alpha by n. Before ionization, before dissociation, again before dissociation, it will be equal to so finally the Van Hoff factor value will be equal to 1 minus alpha plus alpha by n. From that we can find out the value of degree of association. Alpha is given here as I minus 1 whole divided by 1 by n minus 1. So you need to memorize these formulas given here. According to the question, if you are talking about the dimerization, you can apply the formula here. If you are talking about the dissociation, for example in the case of KCl, NaCl and other electrolytes, we can use the previous formula. Clear? So here is one example given here. For example, if you are taking acetic acid in presence of benzene, as we already know, this is acetic acid molecule, right? This acetic acid molecule get dimerizes. 2 CH3COH molecules get dimerized to form CH3COH twice, right? Dimerization happens. So what will happen to the number of molecules here? What will happen to the number of molecules here? 2 molecules converting into 1 molecule, right? So number of solute particles decreases there, colligative property decreases, so that molar mass increases, right? Yes, Nayan, this is a channel from Sri Chaitanya, Infinity Learn. Right. So in the case of acetic acid in benzene, it dimerizes, right? 1 molecule of CH3, 2 molecules of CH3COH is converted into dimerized form of acetic acid. Clear? That is a case of association of the solute particle. So what will happen to the molar mass? Number of solute particles decreases, right? Number of solute particles decreases. Colligative property is proportional to the number of solute particles. So colligative properties also decreases. So that molar mass increases, right? We got the abnormal molar mass here. So we have discussed about the Van Hoff factor, right? Van Hoff factor. If there is any cases of electrolyte, right? If you are having any electrolyte, there will be the chances of association or dissociation, right? Association or dissociation. So that colligative properties changes. So that colligative properties are known as abnormal colligative properties. In order to correct the initial colligative properties, we are using a factor here that is known as the Van Hoff factor, denoted by the letter small letter I. So we can define these equations as 3 types. If you are talking about the colligative property, only, we can find out the value of Van Hoff factor as experimental colligative property, which means our observed colligative property, divided by calculated colligative property, or the expected colligative property is the first equation to find out the Van Hoff factor using the colligative property. This colligative property can be changed from elevation in boiling point, depression in freezing point, osmotic pressure, or relative lowering of vapor pressure, and so on. Clear? Then what about the next equation? If you are talking about the abnormal molar mass, we may expect that it will be just like this, right? But we need to keep in mind that it will be normal or theoretical molar mass divided by abnormal molar mass, which will be in the reverse order, right? Because colligative properties are inversely proportional to the molar mass, right? So it will be equal to normal or theoretical molar mass divided by abnormal or observed molar mass. That will be the equation to calculate the Van Hoff factor according to the molar mass only. Clear? Now the last equation to find out the Van Hoff factor, it in terms of number of moles. If you are talking about any association or dissociation, it will be equal to the number of moles after association or dissociation divided by number of moles before association or dissociation. So these are the 3 important formulas to calculate the Van Hoff factor depending upon the condition. If they are giving about the idea about colligative property, you can use the first equation. If you are talking about the abnormal molar mass, then you can use the second equation. If you are talking about the association or dissociation, you can use the third formula to calculate the Van Hoff factor. Now let us practice some questions, 1 or 2 questions from the colligative properties part. Here is the first question. The first question is, if BaCl2 ionizes to an extent of 80% in aqueous solution, the value of Van Hoff factor is. The value of Van Hoff factor is. This is an electrolyte BaCl2 and it is given as the ionization percentage of ionization or degree of ionization given as 80%. You need to calculate the value of I or the Van Hoff factor given here. What will be the answer? Or how we can solve this? Try to solve the question. We have already seen in the case of dissociation, right? BaCl2 is an electrolyte, so it will get dissociate. How many particles are forming? How many ions are forming during the ionization? Then apply the formula there. You will get the answer of I is here. Okay, what will be the answer? Answer is already given here. At least you can put it in the comments. Answer 2, right? So here is our BaCl2. We need to check how it get ionized. BaCl2, right? So it will be ionized to form 1 Ba2 plus ion plus 2 Cl minus ion, right? 2 Cl minus ion. What is the total number of ions forming here? 1 Ba2 plus 2 Cl minus. So total 3, right? N is equal to 3 here. As we already know, there is a formula to calculate I if there is degree of dissociation happens, right? So alpha value is given as 80%. 80%, right? So if I am converting it into decimal point, it will be 0.8, right? 80 by 100, that is equal to 0.8. So just apply the equation of I is equal to 1 plus n minus 1 into alpha, right? So 1 plus n is given here as 3, 3 minus 1, 2 into alpha, that is equal to 0.8, right? 2 into 0.8, 1.6, 1 plus 1.6, that is equal to 2.6. So option 2 will be the correct answer here for the BaCl2 case. Is that clear? Is that clear? Here is the next question. At 27 degrees Celsius, 0.2 molar glucose solution is isotonic with all the following except 4 different solutions are given here. First option is 0.2 molar urea. The next one 3.6% weight by volume of glucose. Third one 0.1 molar KBr. And the last one 0.1 molar sucrose. Question is based on the osmotic pressure quantity. At 27 degrees Celsius, this particular solution of 0.2 molar glucose is isotonic. I hope you must have the idea about what you mean by the isotopy, how they are connecting with the osmotic pressure. Just recall the idea, then apply it on the question here. Okay, what do you mean by the isotonic condition? Osmotic pressure will be same, right? Osmotic pressure will be same. So if you are taking the osmotic pressure of first condition, right, pi is equal to CRT, where concentration is given as 0.2 molar here, right? 0.2 molar here. If you are talking about the R here, 8.314 into temperature is given as 27 degrees Celsius. We need to convert it into Kelvin temperature, so it will be 300 Kelvin, right? This will be the value for osmotic pressure in the case of first solution, 0.2 molar glucose, right? Now we need to check the osmotic pressure for all the conditions, all the 4 options given here, right? The one point you have to keep in mind that here it is at the same temperature condition, right? At same temperature condition, so we can just neglect the value of R and T here. R and T here, right? We need to check the value of pi according to the concentration only. If you are talking about the first option, 0.2 molar urea, is they having the same osmotic pressure as compared to 0.2 molar glucose? They must have same osmotic pressure, right? Because both the urea and glucose are the non-electrolyte. There is no any chance for association or dissociation of the particles. So it depends only on the concentration. In both the cases, concentration are same, 0.2 molar, right? So it might be having the same osmotic pressure as compared to that of the 0.2 molar glucose. So first case it will be satisfied. Then what about the second case? 3.6 weight by volume percentage of glucose. 3.6 weight by volume percentage of glucose. Similarly, here also you need to check the molarity given here. 3.6% means 3.6 gram in 1 liter of the solution, right? So if you are checking the molarity given here, you will get the molarity same as that of the 0.2 molar. Just calculate that, then let me know whether it is getting the same molarity here. So as according to our case, both the molarities or the concentration are same, right? So osmotic pressure is also same in the case of second case. Then what about the third one? 0.1 molar KBr. 0.1 molar KBr. This is an electrolyte, right? Electrolyte. So it will get ionizes as KBr is equal to K plus Br. K plus Br minus, right? So the number of particles getting after ionization is equal to 2. So there introduces the factor, Van Hoff factor, that is equal to 1 plus n minus 1 into alpha. So here we are assuming it will be 100% ionization. 100% ionization, which means alpha is equal to 1 here. Assume 100% ionization. So obviously alpha is equal to 1 here. 1 plus 2 minus 1 into 1, that is equal to 1, right? So pi is equal to CRT here. I into CRT, I is equal to similar 1 into again CRT. So in case of 0.1 molar KBr also, we will getting the same value of osmotic pressure as compared to the 0.2 molar glucose, right? So in the three cases, we are getting the same value of osmotic pressure. So we can say that all the three conditions satisfy the isotonic solution condition, right? So obviously the last one is the one which is having the different osmotic pressure as compared. Okay, that's all about from my side for today. We have successfully completed our solutions chapter. We have started from the basics of the solution, what do you mean by solute, what do you mean by solvent, how they are depending upon how they are classifying depending upon their physical state, concentration and so on. Then we have seen about some of the terms to calculate the concentration terms like molarity, molality, normality, mole fraction and so on. Then finally we will be moving to the colligative properties here, right? Colligative properties, we have seen about the relative lowering of vapor pressure, elevation in boiling point, depression in freezing point. Then what else? Osmotic pressure, right? Then we have last seen about the abnormal molar mass and Van Hoff factor. I hope I have covered almost all the important topics, subtopics from the solution chapter. So keep revise on the chapter. Make sure that you will be watching all the sessions starting from the first to part 7 for the solution chapter here. Then there is a general reminder for the AATS. Infinity Learn is providing you the All India Test Series for JEE Advanced 2025. So don't miss the opportunity here. Then one more opportunity, that is about the college predictor. You must have idea about your JEE Main scores, right? So you can just apply just add your JEE Main scores in the link provided in the description. You will get an idea about the colleges you will be getting according to your JEE Main scores. That is a big opportunity given by Infinity Learn. Then if you are not getting any good ranks in the JEE Main exam, there will be more opportunities like all the private exams, private engineering exams. Again, Infinity Learn is providing the test series for the WITSAT like private engineering exams. You will get 70% off by using best 70 off code here. So don't miss the opportunity. Enroll fast for all the test series given by the Infinity Learn. If you have any doubt, you can ask. Otherwise, we can just wind up the session for today. I hope you guys enjoyed the session. We have covered almost all the topics from the solution chapter. We have successfully completed the solution chapter from the grade 12. Then in the next class, I will be coming back with them. Tomorrow, I will be coming back with all the JEE Main previous year questions from the chapter solutions. So wait for that. If you really like the session, hit the like button. Share this particular session to your friends. Subscribe our YouTube channel, Infinity Learn JEE YouTube channel, for more updates from the channel. So, what else? Then if you want a session PDF, you can join our Infinity Learn Telegram channel for the session PDF. The PDF will be uploaded after each of the session for chemistry, maths and physics all. Right?